friend has sent me one 2048 environment. So 2048 is basically this game. Let me just show you. It's this game of four squares like this, and then you can move in terms of up, down, left, and right. And what you need to do is to form the number 2048. Of course, you see, you can even get into 4096. So the catch is that when you move up, down, left, right, there'll be a new square that will be spawned. The new square is either a 2 or a 4. Okay, but I think for the code that he sent me, it's only going to be the 2 that is spawned. So yeah, let me just put this thing at the side here. Maybe I use here. All right. Okay. Yeah, so this will give people an idea of what this 2048 game is as I code it. All right, so let us try to do something um, to solve the 2048 game. So by solving, it just means that you do a sequence of moves, okay, such that in the end of that sequence of moves, you form the number 2048, and that's exactly what we want to do. Okay, so let's see the environment. Okay, I mean, this is also one of my first few times looking at it. So accumulate, this looks like you take a function to accumulate. Okay, and then you have an initial variable, and then you have a sequential one. So I guess if you have a sequential one, you accumulate with the sequential at the start. Initial. Okay, I'm not too sure what this actually does, but we'll just skip it for now. Flatten is just actually you can just use numpy flatten. Not sure why they coded this out. This converts a 2D array into a 1D array, this flatten. As 0 is just basically just checking whether there's a 0 in the matrix. Yeah, I think the code could be faster if we use numpy arrays, but let's just see what is being coded here. Transpose over here is a mapping of a list to the map of a list of a zip of star mats. So I suppose mat is the matrix for this 2048 game. So it could mean that, oh yeah, for those who are not aware of this language is Python. Yeah, one of the main languages used for machine learning. Yeah, today I'm using Python because the notebook was given to me as such. I'm trying to code an AI to solve this 2048 game. Okay, so transpose, I look at the function here, is mapping a list to a zip of this star mats. So it probably means that if you have a matrix that is like this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What this star mat does is that it takes in the rows as input. So this, you zip them up. So when you zip them up, you will get this 1, 5, 9, 13, 2, 6, 10, 14, 3, 7, 11, 15, 4, 8, 12, 16. So if you zip them up, okay, they will take the first element from each of the rows, okay, and put them in one output array. Then you do that for the same for the second element, the third, and the fourth. And you do this. So when you map a list of this, you will get this thing. And then when you have the entire list of this, is a is probably going to just be a 2D array. Let me just put this here. Yeah, I guess I'll need to comment this entire thing. So before transpose, then after transpose. Yeah, again, I'm not too sure why this was done like that, because you could easily do the transpose of a matrix. There's a transpose function in NumPy. I mean, I suppose they didn't really use NumPy, but you could just do this transpose function directly, without really going through this very tedious steps here. In fact, I think NumPy will be faster because they implement it in C++, so it's definitely faster. Yeah. Not sure why this was done, but anyhow, yeah, let's continue. Reverse of the matrix is just reversing the you map the row to the list of reverse row matrix. Yeah, so what this does, I can sort of understand how this is done already. So it's like this. So if before reverse was like that, so it's just like doing the, so after reverse you take the bottom 13, 9, 10, 11, 12, 5, 6, 7, 8, 1, 2, 3, 4. Yeah. I guess we could try, to just do it ourselves. So we could do something like this. Map equals to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let me just see what format this is. Yeah, it's a 2D array format. So if I were to try it out and just do my own matrix like this. Okay, and then I do a transpose math. So I get 1, 5, 9, 13, 2, 6, 10, 14. Yeah, exactly as what I thought it would be. So reverse math will be 4, 3, 2. Oh, oh, oh. It's not reverse up down, it's reverse within the row itself. So I was mistaken. So it's like 4, 3, 2, 1, 8. No biggie. Yep. So at least now we are clear about what each of these functions do. Okay, because I believe they will be used for the game logic later. Yeah, if you have any questions about Python that you want to ask me, just feel free to go ahead and do so. Okay, so this is the main functions. Okay, the game matrix is a matrix of n. Okay, n is customizable. So in the game of 2048, the game matrix is a 4 by 4 matrix. Maybe I should implement this in Unity. It might be quite cool to implement the game of 2048. So that could be done as a future project. I think it would take about 3 weeks. 2 3 weeks. Actually, it's just 2 3 hours, but spread over 3 weeks. Okay, so this is the game matrix. We append this 0 times n, which means that the initial matrix is all zeros. Add 2. So add 2 basically just if there's no zero position, then it returns the original matrix itself. If not, it will randomize A and B, and then it will basically randomize the A and B, which is the x and the y coordinates, to choose a zero square, and then that square will be equals to 2. Okay, of course, in the actual 2048 game, there's also add 4. Okay, so maybe we could make this even harder by having an add 4. Yeah, let's just define our own add 4. I mean, if we find the add 2 is too simple, we can also add 4. So if I remember correctly, the actual 2048 game, actually, why not let's just play an online version of 2048. I wonder if this is the game that I could play. Yeah, let's see whether we could get this recent computer game. The problem has been solved. Yeah, that's exactly what I'm trying to do here today. But I don't want to see the solution. It's nicer to code it myself. I just want to play. Okay. I think this is it. Yeah. So initially it's like that. Does it only come out twos or will there be fours? Okay, let's just see. Oh, okay. It looks like the original game is only twos. I don't see any fours coming up. And then actually you cannot move, like here I cannot move left because if I cannot combine my squares, I cannot move there. I can only move in the area that I can combine my squares in. Interesting. I suppose there's some like heuristics to solve this. See, like over here, the 64 is in the middle of two 32s, which is like not exactly that great to solve. There we have it, a redeeming chance, whereby I could possibly get this 64 together. Yeah, there we go. There we go. We got. Uh, so I guess I could do this 16 together. Okay. Yeah. Yeah. There we go. Yeah. Oh, is it once nearing the end, a 4 could appear also. I'm just seeing whether 4 could appear or not. Apparently, no, it doesn't appear. Okay, but at least now I know there's a limitation of your moves. You can only move when you can combine like two squares together. If not, you cannot move. There we go, 256. This interface is implemented pretty well actually. Whoever implemented it did a good job. I wonder if I could actually solve this. Yeah, because I don't remember winning the game before. Oh, it seems to be that I made a bottleneck. Isn't that great? I better remedy the situation. Okay, yeah, at least it's like, oh no, I pressed the wrong button. Okay, it's not that fatal yet, right? It's not that fatal yet. I can still potentially win. Actually, it's pretty cool. I wonder whether there's a heuristic to like play this game, like without even doing look ahead. Can you even win the game already? Yeah, so it looks like only twos appear, which means that oh, you see that one, the four appeared. So when will the four appear and when will two appear? Or is it that the two appeared, but because it combined straight away with a four, it became a four? Yeah, so maybe the 2048 game really only has two appearing. And then, okay, better move cautiously. I'm about to lose already. I can sense it. Okay, I better do something drastic. If not, I would lose. Okay. There we go. We have 256 appearing already. Now I need to find a way to, like combine the 256 together. Mm, we are safe for a while. But because my 256 is like not able to combine, so it's kind of a bummer. I'm not able to combine the 256 together. Do you see that? The 4 just appeared at the top left, which means that 4 does appear like. Okay. Okay. It looks to me like there's a chance to combine those 256 together. Alright. Okay, I need to get rid of. There we go. Yes. Now I made it to 512. Okay, I don't think I can win this game. Yeah, so actually, my friend's AI that managed to do until like 1024, sometimes even 2048, is pretty good already. Yeah, because the amount of possibilities that you need to consider for this can be quite immense. So, yeah, but one thing about this game is that the more you play it, okay, the as in the further you go in the game, the fewer the choices that you can have because the board is already very constricted. So the AI, when they spawn a random position, the random two, is limited to only certain regions because of the way the board works. 16, 64, 1 to 8. Yeah. So I guess this is what he meant by snake position. Am I losing? Oh, that was unfortunate. Yeah. Da, 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 da. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have a feeling that I'm going to lose. This is very, very bad feeling. Hmm. Okay. No, I may not even get to 1024 at this rate. Okay. Don't give up on me now. Um, okay. Okay. Yeah. So actually, if there's a way to constrain where the oh, you can see the board is like sort of filling up. Have I lost? Game over. Okay, I guess I got the hang of it. So it's really just spawning random twos. Yeah. Okay, so let's see. Looks like I don't need to define an add 4 function after all. Add 2 will be sufficient. Okay, game status. So if there's an element that is like 2048 like this, okay, if there's an element like that, then the game will be lost. Okay, if there's has 0, that means there's still a 0 position that's not filled, the game is not over. Okay, and then if let's say we can still combine horizontally or vertically two squares which have a similar value, then it's not game over as well. Okay. Okay, so merge left. Let's see what this element does. So pick element by element leftward for tau in row. If tau is 0, continue. If previous tau is 0. Okay, so basically you just keep shifting all the taus to the left. Okay. So previous tau is equals to tau. If previous tau not equals to tau. Okay, so I get it. If the tau is similar to the previous tau, okay, then we multiply the value by 2. Okay, if it's different from the previous tau, we append that value to that row. So it is essentially it's like adding up the value of that row together. So yeah, that's quite a good way to do the merging. And then like uh We append zeros to the end of it to make it back to 4. Okay, and then return the merge row, and then whether or not the row has changed. Merge row, is it not equals to row? That means like there's a change, and then a score increment. The score increment will be whatever that has been merged. Okay, I get it now. So merge right and merge up and merge down. They just basically reverse the matrix and do the same operation as before. So that's quite a clever way to do it. So the helper functions earlier, the reverse and the transpose, will just handle the case of merge right, merge up, and merge down. So there's a game record here. Make new record. Mat score means like you return. Actually, just return the tuple mat score. Get record matrix record is record 0. Get record score is record 1. So in every record is a tuple, and if you want to get the matrix, we return the coordinate 1 or the tuple 1, and then if you want to get the score, we return the second item in the tuple, which is like index 1. New records is an empty one, and whenever you add record, you append to your records this new record. If num records greater than num undos, record equals to record minus num undos. Yeah, so I guess if let's say we are just storing the 3 most recent records because like we update like that. Number of records. I think this is not that important because it's like recording the score. We're not too keen. I mean, we're not really maximizing the score here. We are trying to maximize we are trying to get to 2048. So we are trying to get to a win state. So the score is not as crucial as getting the win state. The win state is the main thing. So let's see. Game state ADT. So we can make state with a matrix total score history. Get matrix state, get score state, get history state, make new game. This is important. We make a new game like that. And then we execute a move state matrix up data. And then we can also do a left, right, up, down, which basically does our move. Okay, so I guess what's this game logic? Okay, this is the minimax my friend created, but let's just copy and paste this thing here. So maybe what we do is we make a new game. So in order to create the AI, we first make a new game of a grid size of 4, and then while the game status is not is not over, okay, we define some functions, get best move, and then best move equals to game logic best move. So game logic is here. So his get best move is here. Okay, I'm trying to understand how to code AI first before I use I'm trying to use a Monte Carlo approach first to see whether a Monte Carlo approach means just try out all the moves randomly until you get the answer. Okay, but the issue with this is that it's not exactly deterministic because when you move like left, the two will appear randomly. So you see, after you make your move to the left or right, you execute your move. Okay, after you execute your move, you need to add two to your final to your matrix after you move. Okay, so let's see how to get this. Okay, I'm still a bit curious. What is this get best move current state? Get best move is a inbuilt function he did here. Move scores equals to this. Return the move with the max. But why is there another best move equals to game logic best move? Because I get it. So by calling game logic best move, this best move is a string, either left, right, up, down. So when you call game logic with that string, you actually call this like down function. And then when you call this best move current state, you're actually moving the state to the next best move. Okay, so let's just call a function called define random move. Okay, so return. Okay, so maybe we have an we have a index equals to mp.random.ran in. Okay, 3 4. So it means that, so wrong, mp.random.ran in, it will return from low to high. High value is like, for example, 2, it returns a integer from 0 to 1 uniformly distributed. So 5 will return an integer from 0, 1, 2, 3, or 4. So we could do this, and then we can just return up, down, left, right, and then the index here. So instead of get best move, we could just do random move like that. Oh, okay, looks good. So let's see. Print initial states will be equals to this current state. And then at the end of it, we could print final state equals to this one. So this is a list of, okay, so the current state itself, we only interested in the matrix. So yes, first current state has the game matrix, the score, and I can't remember what's the last, and the history. Yeah, we don't really need to know. I mean, if I don't print this out, what's the history? They didn't really say anything. I guess history is not that important. Yeah, so we could just do this because actually for each of these game states here, it is a Markovian in nature. What Markovian means is that it means that the transition from the current board state, like for example here, okay, it doesn't really matter what the previous few histories are. Just looking at this board state alone, okay, like looking at this board state here, I can make my most optimal decision just looking at this without considering anything else. Okay, so the only thing that I need to care about is score. So like total score is here. So one very simple way to do this, okay, is just like I could do each state 100 times. So okay, this one maybe you just call this random AI. Okay, so next one maybe do Monte Carlo AI. Okay, so how do we do a Monte Carlo AI? So like over here, so we have the initial state like that and the final state like that. Actually, it's not very nice to view it like that. Maybe I could do a pandas heat map. See how to do this heat map. Okay, so yeah, I want to do something like this for better visualization. So what we could do is Seaborn heat map data. Yeah, so actually we could do a seaborn.heatmap. So maybe let's define a function called define print pretty or print box state. And then we give a input matrix, and then what we do is, okay, we probably need to import seaborn as S and S or SB. Not sure what people import seaborn as SBN. Yeah, but doesn't matter. We can import seaborn as SB. Okay, sb.heatmap max. Okay, then over here initial state we could just put print box state like that. Okay, am I missing something? So oh, they import as SNS. Okay, maybe we need to do plot.show. Yeah, Seems to me like it's not really showing, but okay. So anyway, people import it as SNS. Let's just use SNS also. So maybe let's do SNS.heatmap. Maybe I'll just do my own matrix. 1, 2, 3, 4, 4, 5, 6, 7, something like that. Okay, so I think I need to import matplotlib.pyplot as plt. Okay, good. So when we do a heat map, we can do a plot.show. Okay, what if I want to put values? So like over here, what if I like this heat map, but let's say I want to do the let's say I want to do something like that. A not equals to true. Okay, let's do that. Annotation equals to true. Okay. Yeah, that's nice. Okay, what if I don't want to show my axis? So uh, what if I don't want to show the axis for this? Let's see. Square equals to true. Okay, let's try square equals to true. Okay, that so okay. I mean, if we were to do something like this, yeah, square equals to true. Let's say I don't want to show the color map. I don't want to show this. I don't want to show the x and y axis. Okay, c bar. So I could put c bar equals to false, I guess. C bar equals to false. There we go. And maybe we could do like maybe since this is a matplotlib, okay, so we could do like plot dot title game state with score plus score maybe like nice. Okay, then I want to remove away my x and y axis. So how do I do that? So let's say I want to remove my x and y axis. I could do c bar ax equals false, I guess. So let's see. Nope. I guess the c bar ax is not the right. No. Remove x and y. This is matplotlib. See how to do this. Yeah, let's try doing this. Let's try to do the set visible. So maybe if I could just do like plots dot get axis plot dot get y axis. Okay, so that didn't work. Matplotlib height axis. Plot.axis off. Oh yeah, oh yeah. That looks more like it. That looks more like it. That that is a great way to show this. Okay, maybe I could change the color bar for Seaborn so that line color. Could I change the C map? Yes. Okay, Seaborn heat map, color map, color palettes. I want to do something like light to dark. See, like starting with like white color. This no, and maybe end with golden color as the value gets higher and higher. Looks more like the original game. Maybe this one, YLOBR. Ah, okay, yeah, yellow, orange, brown, I guess. Why not? Can we do like white, orange, yellow? Okay, I guess it's a fixed name. Can't exactly change it directly. Yeah. Or we could do categorical ones like this. Pet. We could do like pet so that it will appear nice. Hmm. I think this looks good actually. Yeah, so let's just use this thing. So to print the bot state, let's use this thing here. Okay. So instead of this, we do max. Okay. Not equals true, and then games, and then we have another score here. With score. Okay. Convert this to string. Name score is not defined. Isn't it defined here? Oh, because of my alignment. Okay, so current state 0. Current state 1 is the total score. So when we do a print bot state, you know what? Why not we just pass in the current state as, and then in our, here we call it bot state, and then we could have like mat equals to mats. So we could unpack the tuple, mats total score, mat score, and a blank equals to bot state. So we unpack the tuple here. Okay, that looks decent, and then we could like print the bot state at the end. Oh, there we go. Yeah, I'm not sure where this none came from. Oh, I don't have to do a print here. I could just do a print bot state. Okay, yeah, so that sort of settles it. So, oh no, this value over here is like 1.3e plus 0.2. Is there a way to get the value to not Seaborn print values as integer heat map? I think there's a way to this formats. Maybe I would just do like this. There we go. Format equals to D. That kind of worked out. Okay, so if we were to just do like random moves, you can see that we don't exactly break. We don't exactly like go that far. We sort of die out pretty early, and the max um, the max square that we can see is just 128, which isn't that great. So we will need something even more. We need something even better in order to get better results. And so for that, we could do this thing called Monte Carlo AI. Okay, and let's just code it out. So it is pretty simple. So we have four different movements, right? So we have either up, down, left, or right. So okay, so we have current state here. Okay, so what we could do is we could have so for each time we want to do it, so like we could call it num tries. Maybe we call it 1000. Okay, so for move in, up, down, left, right. Okay, so no, we can actually go back to that. We can actually use that as a template here. So we do the for over here. So we call this initial states, and then we have this current state equals to initial state. Okay, for move in, up, down, left, and right. Okay, we need to check whether that move is valid. Okay, I think in this game here, uh, all moves are valid. Like even if there's nothing that can be combined, it seems to be that you can still move. Oh, there's a valid over here. So like when we do a left, we do an execute move state, move left, merge left. Where's my execute move? Yeah, matrix updater. So when we do this merge left, they will return to us valid as a second. So there are some moves that are not valid. So okay, so we need to find out the valid moves. For moves in, okay, then we do move initial state. Okay, so when we do a move initial state like this, we return execute move, which returns the matrix, whether it's valid, and the score. Yeah, but over here seems to just return like the state itself. So there must be something that I'm missing out. So after we return this, execute move state merge down, right? So this would return this one, this one, this one. Oh, it's here already. If valid move, return this state comma false. If not updated state true. So we can just get it from here. So we have valid moves because not all moves are valid, you see. So yeah, actually we could, yeah, I think it's okay to just do a random move here because if let's say the move is invalid, okay, it will just return the same states. It will just return the same states, okay, with a false, which means that we will do the same thing again. So doesn't really matter if it's valid or not. So we could just do a list of valid moves like that, okay, and then if let's say, okay, if it's valid moves dot append move. Okay, so let's just print valid moves here just to check it out, check whether the game is working. Oh, string object is not callable. That's quite a smart way to do it, just doing game logic like that to get the functions. So all four moves are valid. Yeah, okay, so this already filters out all the valid moves. Okay, that's great. All right, so we already have a list of valid moves for every single position in the for every single state. We have a list of valid moves, and then what we want to try out now is we want to do the move with the highest payoff. So what we could do is we could call this function, this random AI function. Okay, we could make a function similar to this, okay, which basically just plays out the game itself. So how do we do this? We could do like this. Find playthrough, okay, and then we have a matrix here, and we have a game state here. Yeah, so just keep playing the game until we hit the end of the game, okay, and then what we'll do is we will then return the score. So best move itself state false. Okay, so actually we don't need to know whether it's true or false. We could just return one. One is the score. So what this does is takes in a game matrix, and plays randomly till the end and returns the score. Yeah, so naturally if we have 2048 at the end, okay, we will get a higher score. So we will just prioritize moves that lead to the higher score itself. So in this case, the score itself is like an intermediary reward function, because when we use the total score as a proxy to how far you can get, like over here, this is 7364. If I were to get like 2048, my score will be way higher than if I didn't. Okay, so we can use the score itself as a proxy to how good that move is. Okay, so this is what we'll do right now. We'll just use this thing to return the final score itself. So this is called playthrough. So we need to do the move with the highest payoff. So okay, how do we do the move with the? So this is, you can call it Monte Carlo move. Okay, and then we need to define Monte Carlo move here also. And actually we don't need like valid moves here. If not valid, continue. Then we can just like continue to the next section. Actually we don't need this. Yeah, we should still use something like this. So maybe we have like score, total score. Yeah, we have matrix called Monte Carlo score. Okay, and this Monte Carlo score will do perform Monte Carlo simulation for each of the valid moves. So yeah, actually we could just do this. We don't even need the valid moves. Yep. Only evaluate for valid moves. Okay, so if the move is valid, okay, then we perform the Monte Carlo simulation for each of the moves. Okay, so basically we need to do a game logic move, current state. After we get this, we will get another state, and we get something there. If we do this, we can do the first move as that move itself. So let's see if we do the first move for that move itself, like that, state equals game logic move. So here we could do like state okay, we current state. I perform a move over here, okay, which will then basically just yeah, if I do this, I could do a function to map this to my current states. All right, so I would have, let's just call this current state. Okay, but this is current state here, so we will call this, let's call it Monte Carlo state. Yeah, because we don't want to influence the current state itself. So then okay, so over here need to repeat this for I in range num tries. Okay, so we have a variable called score equals to 0. We keep doing this, okay, and we take score plus equals to current state 1. Okay, and then what we return is we return the score divided by num tries. Okay, so we will do a playthrough with num tries like that. So in order to do a Monte Carlo state like that, we do this playthrough Monte Carlo states and then num tries. So we get the average score. Okay, so based on this average score, we will then get the, okay, so maybe we could have best score equals to 0. Best move equals to length. Okay, so Monte Carlo score equals to this. If Monte Carlo score is greater than the current score, is greater than best score, which it would be for the initial one because the score is 0, and the score is always positive. So what we will do is we will update the best score. It will be equals to this version of the Monte Carlo score, and not only that, the best move will be equals to the move itself. And then at the end, we do the move with the highest score. Okay, I call it payoff because that's in reinforcement learning. We call it payoff, but highest score is fine also. And over here, we have the best move already, so we could just do the move like that. Local variable current state reference before assignment. How come there's a random move here? Oh. This is game state, not current state. I guess I could create another. I think it's best not to call it current state, although I don't think it. We could call it new state equals to this. So new state equals to game state, and then we keep repeating this. If it's not done, okay, then we do a random move to the new state, and then we update the new state accordingly. And then the score will be like that. Okay, so this was simulate 1,000 times for the various games, and then at each point of time it will just print the best move. So maybe I could do like intermediate printing to see how print the best move is best move, and then I could just print what state, current state here in intermediate printing. So we could see like how long it takes for the game to move. So Wow, takes so long to do 1,000 playthroughs of random playthroughs. So this is just doing random moves. I expected it to be a little faster because like these random moves don't take very long actually. Yeah. Just wonder what's get matrix. Get matrix is probably the it's a state one. Yeah. Oh wow, it's taking so long to evaluate the move. Let's just try it like one try for Monte Carlo. Do the move with the highest score, game logic best move. So the best move is right, and then I'm doing it correctly, right? Up, down, left, right. Why is there an issue here? What's wrong? What's wrong? Come on, you can figure it out. Why can't I get the move with the highest score over here? Mm, okay, logic best move. Let me try to figure out what's wrong here. So over here we do have a move called best move equals to game logic best move. So why is this not working here? Mm, so it printed out right. So I need to like go to the right over here. That's my best move. So oh okay, this is actually best move without the underscore. It's a little confusing here. So maybe I would just avoid this entirely and just just do this game logic best move in one step like that. Just to make it less confusing. There we go. Oh, best move right. The best move is always right, is it? Which is something wrong, okay, because we don't really want the best move to always be right. Left, down. Okay, so there's something wrong here. The best move is always right for this. But over here, we cannot go right anymore because of the it's not valid. So how can a not valid move be given as the best move? So something is wrong here. So try to see what's wrong with this. So in the Monte Carlo AI over here, if not valid, continue. I know why, because of this best score and best move should always be done here. Yeah, so in the while loop I need to reset the best score. Yeah, so now it's working. It just evaluates like one potential like random future and Oh, with just one random feature, it managed to do pretty well actually. It reached until 128 already. Oh, just by simulating one single Monte Carlo game. Oh, it's actually getting pretty far. I wonder if we can get 256 just with this. Still playing. I must say it's doing beyond expectations. Took even got to 512 just by doing one single random simulation. It looks like it's gonna die actually. Yeah, so if we could have somehow doing an optimal policy for this, it would actually perform better. So has it died yet? No, it's still playing. Still playing the game. Oh, okay. You reach a point of time where there's no move to go. Like the best move is a blank. I guess the score that is written here, like the score that I'm using for the Monte Carlo AI, this score here, um, this score, when I return new state one, this total score, could it be that it's less than zero? Or, so maybe I should make my best score like -1. Then maybe I don't print the best move for each of them. I mean, I could print the best move here with the score. Okay, so maybe I could do this print best move like that, and then score. And then the print board state for this I take out. There's a lot of moves indeed. Okay, so in the end it died here with 2268. Okay, so let's see if I increase the number of tries to 100. Yeah, it's taking a while because the Monte Carlo simulation, if you were to do it per move, it can be quite yeah. I would say that the AI for this could take a while. So if you do like 100 simulations for this, it's not exactly that great because the number of branches for this game is quite high. So just a naive Monte Carlo approach like that would easily lead to an exponential increase in runtime. Okay, maybe I don't do 100. I just do 10. Maybe 10 games is enough to determine how good it is. So 10 games of each, so it's like 40 games. So yeah, you can see that it's steadily increasing in the score. Yeah, here we didn't really use extra heuristics like number of blank spaces and stuff. We could use extra blank spaces as a way to increase the score as well in order to get them to like be guided towards the better outcomes. Yeah, so this minimax actually looks pretty good as well. I mean, it could get 2048 sometimes. Let's just see how far this algorithm would work just by going. So the Monte Carlo is more and more accurate towards the end, which is important because towards the end is where the majority of the states need to be played out. So maybe instead of doing by number of iterations, we could also do by time. So if let's say we have more time to evaluate, we can evaluate deeper in the Monte Carlo search. Yeah. Oh, actually, it's performing pretty well with just this 10. Look, it's going. Look, my score best was 7364, right? Just using Monte Carlo with 10, it easily easily beat my highest score already. And actually, it looks to me like this might be able to solve the 2048 problem. Look at that. Whoa, with just 10 Monte Carlo simulations. Uh, Amazingly, it beat my best score that a human was playing. Human, which is me, was playing. And then, that means I kind of suck at this game, right? If the AI could be so efficient at it. It hasn't died yet. That's that's really pretty amazing. Yeah, but it's taking a while. Oh, it died at 1024. Yeah, so okay, so that was with 10 simulations. Okay, let's just, not print out the best move. We see how long it takes to print out the final state. Okay, so with 10 simulations, I think it's taking a while to do that. But at least I know that this, like, even this Monte Carlo search with just 10 tries could be quite powerful already. Yeah, so we just basically take the valid moves for each of the current state, and then we just find out what is the best average score if you were to take that first move, and then you just keep doing all the random moves all the way to the end. You see what's the score that is being printed out. So yeah, indeed it's taking a while. So maybe 10 tries is not that great. I mean, if you look at the minimax version, the get future score with the decay, actually this one is not too bad also. It's not printing out the final state. It means it's taking a bit too long. Okay, let's just try making the num tries to maybe, I don't know. Let's see. Num tries to about 5. Okay, then let's just print out the score with the best move. Or we could just print out the score, current state 1, and then just end it with a space like that. Actually, wait. Maybe I just print out the score, and then we can just print this once. So like the score, print here. Yeah. So that we can see like the progress of the algorithm, like where is it at. Not too bad. Yeah, it's pretty fast with 5. But I guess it doesn't work all the time. It's probably, in order to get this to work all the time, I believe that there needs to be more efficient algorithm, and maybe like even for the starting states, we could even use like heuristics to learn how to get there. So you can see that it's ended off at 512. Let's try again. Maybe just having 5 states, it may not be sufficient in order to learn. Maybe I should do one with 100 and see whether it works. So if given enough compute time, like infinite compute time, it is potentially possible to get the 2048 answer. Oh, I think this might solve it. Oh, that was so close. We reached 1024. Which is actually not bad. I mean, you look at this, with just a normal, I mean, if you just look at the random move AI, it's 640. It's like almost a tenfold increase in score just by doing Monte Carlo search. And Monte Carlo search is really just taking the first move that is a valid move like this. And then we just play through like 5 more times of that, average the score, and gave such a big improvement. Okay, so now comes for the time of reckoning. Let's just put it at hundreds. Okay, it's not really moving, so 100 maybe is a bit too long. Is it moving? Is it moving? Is the score moving? Yeah, it's creeping really slowly, but it is moving really, really slowly, I guess. Yeah, it's moving, it's moving. Yeah, but really, really slowly. Yeah, so 100 means that I try out this port state 100 times, and then I just pick the port state with the highest score. Okay, and based on that, we will then perform the next move, and then we keep doing this evaluation again and again for the future moves. Okay, so yeah, now I have a feeling that for the initial board, right, perhaps I could just just do random moves for the first 20 moves and I can still win the game. Thinking something like that, because the first few moves actually doesn't matter. Look at this. I just do like that, just like left right left right left right left right. Okay, the first few moves don't really matter that much because you can always combine quite easily. Oops, I died. So that was 1312. Okay, so I'm going to just head out to the toilet for a while, and let's just see whether this using 100 tries per move, up, down, left, or right. So the initial move is fixed. Okay, because we run through this Monte Carlo state once, which is like we move already one time, and then based on this Monte Carlo state, we play through this number of times, number of tries here, and then we do an average score. And based on the average score, we will then choose the move, the first move that based on the average of the 100 moves later, we choose that move that gives the highest score at the end. So that is something that already gave quite a big improvement just now with just even 5 tries. Even with one try actually, that Monte Carlo estimate was actually pretty good already. It was almost like 10,000. Already beat the human score. So it's actually pretty powerful if it beat the human score. Yeah, so it means my score sucks. Yeah. But yeah, let me just let it run for a while. I'll be back in like 5 minutes to just take a look at how it is. Okay. And yeah, let's just see whether this works. Maybe 100 might be a bit too long, but is running really, really, really slowly. But I believe it will run faster and faster as the number of, because you see the number of bot states, there's like close to 40 to 50 bot states that needs to be implemented before we can even reach 2048. But towards the end, with these 100 moves, it will be more and more and more accurate. So maybe I could have a temperature that goes like based on the number of moves. Okay, so this num tries could not be fixed. It could be fewer at the beginning because at the beginning you can't die that easily. Okay, and then maybe at the beginning you can just have it as one, and then towards the end you increase that more and more. Or we could have a timer here. Okay, and then as long we can set a certain number of seconds per move. So maybe it could be like 1 second per move, maybe, and then we evaluate as many bot states as possible in that 1 second. Okay, so if it's 1 second per move, then we will need to check how many valid states are there, and then we divide our time equally between all the valid states possible. Okay, so yeah, so this could even be evolved even more to do like later on we could do something like Monte Carlo tree search, where at each point of time we just search the node, okay, that gives the highest promise in terms of the expected value, and then we keep searching that, and then we have another constant term that is the exploration constant, which is like number of times we've visited that node. The longer we haven't visited that node, the higher the chance we will visit that node next. So we could do something like Monte Carlo tree search. Okay, just for the first node only. We don't really need to do for the tree. Although if we really were to do Monte Carlo tree search for the entire tree, that would be best. But given the number of tries and given the number of tries that we have here, it doesn't seem very feasible to implement Monte Carlo tree search for the entire tree. But I think we have to go somewhere into the Monte Carlo tree search area because just a simple Monte Carlo takes too long. See, now it's at 11960. So with 100 tries of Monte Carlo, I'm trying to see whether this actually can get a good score. Yeah, I'll be back by 5 minutes. Let's hope that this works. Wow, it's been 5 minutes already, I guess, and we still haven't gotten the answer yet. But as you can see, the score is increasing rapidly, and it looks like the depth of this search is close to 100 or even 200. It's really quite extensive, so it is it is not that easy to get this to work just by purely using a Monte Carlo approach. So indeed, this problem can be quite tough, and that's what makes it exciting. I'm going to solve this. Yeah, after this, I'm going to use Monte Carlo tree search type like approach in order to do it. I mean, you look at this like minimax algorithm that my friend coded. Get future scores like that. And then append the future score. If not, score difference. Yeah, so he did for like 3 steps ahead and get the best scores for that. Yeah, so he didn't search all the way to the end of the tree, and that is a possibility to just like basically we just prioritize gaining scores as fast as possible. So he didn't search the end of the tree; he searched for 3 steps only, 3 steps ahead, and then he just found the best move, which is he got the score that gives the best move 3 steps ahead. It's not really minimax, actually, it's more like max max. Yeah, I know how he did it already. He just took the score for the next 3 steps. It's not really a minimax because there's no minimizer. It's just taking the future state like that. Which gives me an idea because since we have this proxy reward function, which is the total score, we could potentially use the total score and then just say that at every move we are trying to be greedy. We try to maximize the total score. So um, we try to select moves that maximize the total score. So rather than searching all the way to the end of the tree, look at this. Every single search that we do, we need to search. Like I think the depth of this tree might be the whole game tree. The depth might be close to 200. You look at the number of numbers that appear on the screen. The depth of this game tree might be close to 200, and because of that, uh, it is going to be tough to actually code out like the entire game tree and search thoroughly. So if we could like truncate the game tree and have some sort of heuristic to give us the score. So I'm thinking the score itself, one heuristic that I could think of is that like what are the number of like empty squares available. Each empty square could be worth 100 points, 200 points maybe. We could adjust that heuristic, and then based on that heuristic, because the amount of empty squares left will tell you what is the amount of potential moves you could make. The more empty squares, the more moves. Yeah, so we could use that as a heuristic. And then like even the stuff touching each other, like two consecutive eight touching each other, we could just count that as one square, because like two squares touching each other with the same value, um, it could be counted as one square because you could combine them in the next move. So yeah, stuff like that could be factored in, and like whether or not like the larger board states are touching each other. So there could be a heuristic function that we use to evaluate how good is a potential board state. Like like this board state, like 128, 32 is not touching each other, it's not very good. Like none of them are touching each other. So this is like a dead board state. So you don't give extra points. But yeah, you could have a heuristic function to score your board state. That could help it to work better. Okay, so I'm just curious, a naive approach like this, I call it naive because I didn't do any heuristics. Okay, the only thing that was done was just a Monte Carlo simulation to just tell us how good each of these moves are. Okay, I mean, if we really wanted to, we could even input this thing in a neural network in order to find out the heuristic. So it's going to be something like alpha 0 or DQN. DQN, yeah, we could do something like DQN in order to find out what is the like the the QSA of each move. So DQN does it by this QSA. So like the Q function of a particular state and a particular action. Then we could find out what is this value here, and hence from there we could like figure out what is the best action to do. So we could do something like a neural network to score the state itself using reinforcement learning. Okay, so that is indeed possible. It's indeed possible to use DQN to do it. Yeah, but I think over here just using this naive naive, what do you call this? This is called Monte Carlo. I think Monte Carlo, but probably truncated that, because right. So if I were to truncate the depth at maybe a depth 5, I have a feeling this will work quite well, because like in num tries 100, you do until depth 5, it won't take up too much compute. Right now, the depth is like is very high actually. Look at this. I think this is at least 200 numbers. So yeah, you see that the algorithm has run for close to 10 minutes already, and the score, it has beat my max. The human max of 2048, or rather my max of 2048 is quite low. 7364. Yeah, but to be fair, I haven't really played this game for a while. Yeah, I guess I could do better if I try again. But it just took too long. Oh, look at that! It hit the 10K, hit the 10K mark. The score that our AI is doing for Monte Carlo, it hit the 10K mark already. So if we do Monte Carlo with a bit of tweaks, like prioritize exploration of nodes that hasn't been looked at before much, or prioritize nodes, or prioritize the first move that gives a higher score overall more, that kind of thing. If we prioritize our search in that way, we could potentially solve this game. I'm quite sure of it. And then we could also like cut off the search instead of doing all the way to the end, which takes a lot of time. ideally this is the best, of course, but we could just cut it off at like maybe a depth 5. Yeah, we could implement a depth limited Monte Carlo, because we do have this thing called total score, and that total score can be a proxy as to how good the board state is. And if we wanted to, we could also add in like extra points for the number of blanks, number of zeros that are in the board, and maybe 100 for each extra zero, so as to incentivize the AI to like fill up the board. Yeah, but if we incentivize too much for each of the blanks, we might get a state where like you fill up very fast, like all the blanks, like you get 16, 32, 64, 128, but you cannot really combine them together. So that is not exactly ideal also to like to incentivize the blanks. So it is best not to like add in the blanks as a heuristic, I guess. If you might prioritize short-term gains, but the AI may not be able to solve this game overall. I think it's going to solve this. Like like if num tries 100, I think AI is going to solve the game. It's just my gut feel. I mean, it has hit the 11K mark, which is good going, I guess. Good going. Yeah, I wonder if this AI could even reach 4090. Theoretically, 4096 is possible as well for this 2048 game. It's just that 2048 is tough enough for most people already. So that's why the game is called 2048. Okay, let's pray hard. Okay, so it has been 15 minutes since I started running this AI. It's definitely too long. Okay, but this is just to show you, like, I'll show myself how good a pure Monte Carlo, which is just like random search algorithm, can do. So you see, towards the end, it's evaluating really fast. It just means that it either has found the correct 2048 solution, or it has like committed suicide. It looks like it's still going. Means there's some potential that it can actually solve it. So let us hope for the best. Let us hope for the best. It's gonna hit 14K soon. This is quite exciting actually. It's like watching the stock prices rise. Oh, look at that! Look at that! Okay, it's combining. It's combining. Yeah, actually kind of slow, because you see, if every move you only add in a two break, right? You need to, in order to get 2048, you need 1024 moves. Yeah, I mean, if you think about it, if every turn you only add in one break that is consisting of a score 2, you need 1024 turns in order to. So the depth of this search tree is 1024. Wow. I mean, unless you die early, but yeah, 1024 is depth of 1024 is kind of hard to do a Monte Carlo tree search actually, because the a tree of depth 1024 is kind of unimaginable. Yeah. Imagine if you have 4 valid moves per depth of the tree. So what is 4 to the power of 12024? Let's just take a look. Let's say you have 1024 moves. 4 to the power of 1024. Let's just search 2 to the power of 1024. You just times 2 this value. Oof, look at that. So this is the number of moves possible with a depth 1024 tree, which is oh, holy, 10 to the power of 616, 617 decimal digits. If we were to if we do 4 valid moves for each of the uh 4 valid moves for each of the depth of this game, you will get a total of 10 to the power 616 possible moves. It looks like it's going to solve the game. I have a good feeling here. I mean, if it reached 16,000 points, I'm quite sure it will solve the 2048 game. But it's taking a bit too long. So far, the runtime for this is close to 20 minutes already for this algorithm. Okay, it's ending, it's ending, it's ending. Look at the score, it's ending. I mean, if you didn't know better, you would think that the game has hanged, but the AI is indeed solving it. It isn't that bad in AI actually, because like for each move, it takes less than 1 second. Just by doing 100 random evaluations, the game of 2048 can be solved pretty well using Monte Carlo. Yeah, but if you talk about overall solving of the entire game, then I guess if you have 1024 moves and each move takes 1 second, we could count how many seconds it will take. It will take 17 minutes. So essentially, this AI, if we were to solve the game, it would run for a total time of 17 minutes. So it's around there. So I think it might be solving the game already, because it is indeed getting a total score that is higher and higher and higher and higher. Okay, it's ending. I can feel it. Yeah, it's ending already. Oh, he still didn't solve the game. Oh my gosh. I thought it would. Yeah, I thought it would solve the game. So even with 100 random moves, uh, I mean, it achieved quite a high score. It achieved a score of 19,000, which is three times my human score. So it is a pretty good achievement already for the AI to do that. It's just unfortunate that even with 100 random moves, it failed to solve the board. But it did reach 512 and 512. Okay, it just failed to combine these two 512s together to 1024, and then combine these 1024 together to get 2048. So it was very, very close to solving already. Okay, so maybe you could make the AI a bit more efficient, but let us first try to solve this 2048 AI. And yeah, maybe I'll continue this tomorrow. This is an interesting problem to solve, but I've got to go now. And yeah, if you have any ideas on how to solve this 2048, you can do drop them in the comments. Okay, but if not, see you all next time. Bye bye.